Alrighty, continuing forth. Let's see. So we're continuing wrapping up waves and going to start a very brief run through of some of the results of thermodynamics. Just to give you some context to see kind of how everything we've been doing this semester can also be used to describe the very small, which is where thermodynamics plays an important role. But to review, we were talking about standing waves, wave patterns that are set up such that they keep the constructive and destructive interference patterns set up waves where there are regions of calm as well as regions of, this is the vibrating string, yes. Regions of calm and regions where you're getting perfectly destructive interference, those are called nodes. And then regions where you're always getting constructive interference, those are called antinodes. These standing wave patterns are why music essentially works. You can think of these standing waves as the set of tones and frequencies that are created when you, say, pluck a guitar string. I send various, when I pluck a guitar string, I send waves moving along the guitar string in many directions. Many of them will end up canceling out with one another, but there are a given set of very precise frequencies, or you can think of it as a set of very precise wavelengths that create standing wave patterns with themselves. In those cases, like what we're seeing in the image, the amplitudes can sometimes work together and create a resulting overall wave that has a much larger amplitude. And that if that wave is then allowed to propagate into space, through the air, out of an organ pipe, across a guitar string, whatnot, that can produce the sounds that we hear and the particular notes that we hear. So last time we talked about for closed systems, so systems that are anchored at both ends, like a guitar string, where in this case, by looking at the standing waves, you are looking for the waves that satisfy the relationship that they are always antinodes at the endpoints. The two closed ends are always antinodes. The longest possible wave that fits that requirement in this case is the one where it only undergoes half a wavelength from node to node. This is the longest possible wave that could possibly satisfy it being fixed at both ends. We call this the fundamental node, or the first harmonic. Turns out it is the note you hear when you play, when you pluck a guitar string, or when you play a particular piano key. The reason that a particular piano key might be called C sharp is because when you play that piano key and a string is plucked inside the piano, the fundamental frequency that string is vibrating at corresponds to C sharp in that case, perhaps, and whatever that frequency is. So we stopped last time by realizing that there was a set of frequencies that were possible if I have a string that is of length L. The wavelengths that satisfy this requirement is ones where the length L is equal to half the wavelength, one wavelength, 1.5 wavelengths, 2 wavelengths, etc. And so we're able to write down a general relationship that for each harmonic, n can be 1, 2, 3, 4, 5, whatever, this is the wavelength of that wave. Then taking a step further, we could translate that into a frequency if we wanted to. And I do that here, where the velocity of the wave, which is determined by the medium, by the string, by the air, is equal to the frequency, which relates to what you hear. The frequency of a note is what determines what note you perceive it as, be it C, C sharp, C at a higher octave, higher pitch. The frequency is essentially telling you the pitch. And the wavelength that note has on your instrument, be it a guitar string, the wavelength of the air passing through your flute, what be you. And so the frequencies for a given string of length L that has a wave speed V, for closed systems where it's fixed at both ends, this is the relationship between the frequencies that frequencies that you hear and that are possible at that wave, at that for that string with a given wavelength, which you can write in terms of some number n, which is 1, 2, 3, 4, 5, whatever, multiplied by the fundamental or the bass tone that you hear, the bass pitch that you hear. If this is a 440 hertz instrument, that means it's going to play middle A. That means that the F sub 1 is 440 hertz. Which then means the, oh dear, I wrote this down wrong. Look at that. 2 first harmonics? This is nonsense. Erase this. Second. Third. So this means also if you wanted to look at the higher harmonics, if the bass note is 440 hertz, then that's the first harmonic, then the second harmonic is 2 times that, or 880 hertz, which ends up being an octave higher. Octaves in music are doublings in frequency. So middle A might be 440, and A an octave higher, which is the same kind of note, but it is a higher pitch, is 880. The third harmonic then is 3 times the fundamental, or 1,320 hertz. And then it goes on from there. So let us look at what this is like, this relationship is for other instruments. And then also think about the relationships between some of these variables. Some of these we can do, one of these we can do already. Let us take, let's just look at the relationship between whatever the fundamental frequency is going to be and the properties of the string and the wave. So in that case, it's just V divided by 2L. Gives you the frequency of the wave, or of the sound wave that you're experiencing. So in this case, if I look at, I have my little chromatic tuner. If I play a particular note, on a string, and it says that it's playing C, that came about because my finger is holding down the fretboard, at this location here. I'm essentially holding the string fixed at this point, and it is being held fixed at this point here. So this is determining the length of the string, which, if you look at the formula on the screen, also says that for a given sound speed, which relates to, say, the tension that's in the string, that corresponds to a particular note. So that if I reduce the length of the string, so now I'm going to move up, a couple frets, going from here to here, I have now reduced the length of the string, so the pitch has increased, or the frequency that I hear has increased. The denominator got smaller, the pitch, the frequency got higher. Right, keep going. So again, I'm just shrinking the length of L, and that is creating a higher fundamental pitch that I am then registering. The whole idea with tuning, if I play just nothing down, just play an A. That A is the note that corresponds to the length of the string from here all the way down to here. That corresponds to the length of the string. And then there is some tension set up in the string such that waves move at a certain speed down the string. If I reduce the tension in the string, the pitch ultimately ends up going down. What I'm doing, I'm reducing the tension, I'm reducing the wave speed, so the pitch goes down as a result. Still out of tune. Still out of tune. Now I'm increasing the tension in the string. There we go. So increasing the wave speed, which in this case might be increasing the tension in the string. Increase the wave speed, increase the pitch of the fundamental tone that you hear. Decreasing the length of the string creates higher pitches as a result. In this case, not all strings are created equal. Some of these strings are thinner compared to some of these other strings. This third string here is actually quite thicker, which as a result, even though the length of the strings are the same, this string is, it's probably too hard to see, but this string is much thicker than, say, this string. So when I pluck that string, it's a much lower note, which is as a result is that the mass density of the string is much higher, the wave speed is much lower. So as a result, the denominator gets small, and then for the same L, but now a smaller wave speed, the note comes out at a lower pitch compared to. So that actually is the same note, but different octaves. Low C, high C. The frequencies, if I were to calculate the frequencies between these two notes, the frequencies would be some multiple of each other. This frequency, if I multiply it by 2, I might get something that sounds like this. So what about different instruments? Take a trumpet or a flute. A trumpet, you blow air through one end, it does some stuff, and then it ultimately comes out the other side, in a larger hole. In this case, you're blowing air into a large opening, and then air is exiting out of another large opening on the other end. All right, this is kind of the idea. Let's see, does this work? I guess this is not quite right? This is open, this is open on one end, but not open on the other. But it's the same idea of kind of what you do with a flute. Versus a trumpet, where you have to buzz your lips to perturb the air and start the air inside the trumpet vibrating. So these are examples of open systems, where there's nothing clamping down whatever is vibrating, in this case the air, on either end of the instrument. You blow into one end of the flute, kind of through a large opening. The sound then reverberates within the flute and then exits, throughout the flute on the other end, which is also usually open. So for open instruments, usually in this case, now we're not dealing with things like guitar strings, we're actually doing something to the air that is inside the instrument, by blowing through the hole of the flute, or by buzzing your lips, about the one end of the trumpet. You are perturbing the air directly in front of you, which is causing the air to start to vibrate throughout the trumpet until it eventually exits the other side, or the flute exits the other side. So where for closed systems we had said that the endpoints always have to be nodes, for open systems, the endpoints are always antinodes. And typically we see these cases for instruments that are trying to propel air through a device, through the flute, through the trumpet, whatnot. And why it's important to be an antinode at the end, I might be able to explain. Let's see, I can think of this as a flute where there's an opening on one end, then eventually comes out, on the other end. where the opening is much bigger than the wavelength of individual waves, so you can think of it as a big open hole. In this case, it is important for the wave that's set up to exit with antinodes at the end, because if not, we would not actually be able to hear anything that comes out of the instrument. What's going on is that you are perturbing the air inside, say, this cylindrical pipe, which we'll call a poor man's flute. Remember that sound is an example of a longitudinal wave. It's not actually ups and downs like what I've drawn here, but there are regions where the air has become compressed and regions where the air has become kind of more spread out. And those compressions bounce around the flute and eventually try to emerge. But remember, just like with transverse waves, every individual air molecule is not actually going very far. They're just kind of jiggling in place, and sometimes they find themselves compressed, sometimes they're allowed to spread out, and that's what they're seeing along the pipe in this example. Some organ pipes can also be thought of as open-open, depending on how they're developed or built. So where there's large oscillations, in this case, in this antinode, there's a large oscillation. There's, it goes between compressions and rarefactions at that spot, because it's going up, it's going down. If you think of the transverse analogy, the wave is going up and down, and it's going through all sorts of possibilities. For the longitudinal wave, it's going through compressions, rarefactions, neither or both, and is going back and forth between them all. Versus at the nodes, where the air really is not moving. Individual air molecules are not really changing their location at all in terms of feeling themselves compressed, pushed apart, whatnot. So there's much less jiggling that's going on, which means that then they collide. They essentially are just kind of a conduit, for what's kind of going on around them, as the pressure wave kind of moves, left and right through the pipe. And so if you want sound to come out of this instrument, you need to perturb the air outside of the instrument so that that sound wave travels out into the room or whatnot. And you can think of this, if you think of, since sound waves are a series of compressions and rarefactions, you can think of the air at this location here at the very end. Those air molecules are the ones that are jiggling around to the left and to the right and are eventually colliding with the air that is outside of the flute or the organ pipe or whatnot. So they are the ones where if a wave pattern is traveling, they are transmitting, that wave energy is transmitting through those particular particles. There needs to be some sort of disturbance as they connect with the outside air, so that then the wave continues to move into the air in the room, in the nave, and wherever the instrument is located. Versus if that was always if that was always a node, then the air that kind of creates the membrane between the air inside the instrument and outside the instrument would be remaining effectively pretty stationary. There wouldn't be really any perturbance with the outside air, and no reason for the sound wave to then propagate outside. So in this case, it again becomes the same question of, I have two endpoints that are separated by a length L, the length of the flute, the organ pipe, what have you. And I want to come up with what are the standing waves, what are the waves where I can expect this nice kind of resonant pattern of construction and destruction to create a nice big standing wave. Now with the constraint that both ends are open instead of both of them being closed. Turns out it's essentially the same answer. The first example might be something like this. Again, half a wavelength, where essentially it just oscillates like this. One end is up when the other end is down, and just goes back and forth. So in this case, L might be the fundamental tone over 2, again, like what we saw before. Another example could be, this is an example that satisfies the requirement that both ends are open. So the endpoints are going kind of, in sync with each other, going up or down, while the stuff in the middle is going in the opposite direction, down or up, and it oscillates in that regard. So in this case, it looks like L is 3 lambda 2 over 2, and 1.5 wavelengths. Where the next one might look something like this. And we essentially get to the same sort of answer that we were getting at before. Sorry, this was supposed to be a 2. This was 1 full wavelength. Where this is 1.5 wavelengths. So you ultimately come up with the same answer that you had before. So we could extend what we had before and say for open, open, or close, closed, the standing wavelengths that you can expect to hear are given by 2L over N, where N equals 1, 2, 3, etc. So then as a result, the frequencies you would expect are NV over 2L, or N times the fundamental frequency, the first harmonic. Then there are other cases like, say, the woodwind family, where you have some sort of woodwind mouthpiece, which is a very small closed opening that essentially you're plucking the reed, the piece of wood, and that is causing the air immediately behind and in front of the reed to start vibrating. And then that propagates through, say, the saxophone, and then exits through a big opening on the other end. A clarinet is the same way, and again, some organ pipes are devised this way. Essentially, when you have the big organ pipes, where then air is being blown through a small hole at the bottom, that can sometimes be treated as a closed open system, like this. So this is an example where one side is closed, where the other side is open. So the woodwinds are examples of various organ pipes. And the requirement here is that if we're looking for standing waves, the requirement is that, over some length L, the requirement is that one end remains fixed while the other remains open. And similar to what we had above, it being open, since that is usually the opening that the sound wants to then move into the air of the room, that opening we always want to be an antinode, and for this side we always want it to be a node. So again, we can ask ourselves, what possible wavelengths work in this case? The first one is not half the wavelength like what we saw before, but it's the quarter of a wavelength. You can imagine the string oscillating up and down. Essentially, it goes from a middle point to either a peak or a trough, and that entire thing just moves up and down as one. So in this case, the length L is equal to 1/4 the wavelength that could fit across this length L. The next one is not, before we just kept upping it by 1. So the next one you might think might be half a wavelength. But half a wavelength doesn't work, because half a wavelength means it comes up and then has to come back down. But we require that the endpoint be an antinode. So it's not a half of a wavelength doesn't work, but 3/4 of a wavelength works. So it comes up, it comes down, and complete a full wavelength. So then the oscillation would then look something like this. It would oscillate up and down between the blue curves. In this case, L looks like it's 75% of a wavelength. Bumping it up, a full wavelength does not work because then you would start at a node and end at a node, but we need to end at an antinode. So in this case, the next one that works, that can start at a node and end at an antinode, is 5/4 of a wavelength. You got the full wavelength here, comes up, comes down, comes back to where it started. That's one full wavelength. Then you got an extra quarter of a wavelength. So it looks like L is 5 lambda 3/4. You might be noticing the pattern that's emerging here. So in this case, it looked like L was either 1, 3, 5, and indeed it just continues 7, 9, etc. n/4, where this is the value of n. So in general, we can say that L is equal to n lambda n/4, where n is odd. 1, 3, 5. Odd numbers. Those are the only ones that fit to create a standing wave that has a node at one end of the pipe and an antinode on the other end of the pipe. So then similarly, I can write that the wavelengths possible are 4L/n. Again, we have to be careful, n is odd. Or that the frequencies possible are going to be NV/4L. Or again, n is odd. So slightly different combinations are possible, and this actually plays a very important role in what's called timbre. The richness, the feel that the sound has. It's the reason why a piano, when you play one note and you play the same note on a saxophone, while they clearly don't sound exactly the same, even though they're playing the same note. Some examples for. Right. If you have a trumpet, a trumpet plays a note at 440 hertz. What are the second and third harmonics of this note? Trumpets are open-open systems, where above for open-open we wrote that the harmonics are just n times the fundamental tone. That's actually true. That's actually true for both. That's a general relationship. You just gotta remember for open and for close, n can be 1, 2, 3, 4, 5, etc. For open close, n can only be an odd number. So by the trumpet playing a 440 hertz note, you are saying that the fundamental tone, the first harmonic, is 440 hertz. So then the second harmonic is going to be 880 hertz. The third harmonic is going to be 1320 hertz. If instead I asked what could an organ do, where we're treating an organ as open-closed, then this is still true. except n has to be odd. So in this case, there is no second harmonic. There is no second harmonic, but there is a third harmonic that can be played by that organ pipe. That organ pipe, when it plays 440 hertz, you hear 440 hertz. And then on top of that, you don't hear the 880, you don't hear the 1320. Those are not possible to also be heard when you pluck a particular string or note. I could ask, you're designing an organ. You want a pipe so that the fundamental tone of the pipe is only 48 hertz. How long is the pipe if you take the climate control in your church or whatever to be 343, to have the speed of sound be 343 meters per second? In this case, this ties into the relationship between the fundamental tone is then just the sound speed or the wave speed. And then for an organ, which is open-closed, it was 4L in the denominator. So in this case, that means the length of the pipe needs to be the speed of sound divided by 4 divided by the fundamental tone. This ends up being something like 1.79 meters. If you were to construct a pipe that could play at its fundamental tone, something that is 48 hertz. Now, what do these harmonics mean? What role do they play, if at all? A tone that I could generate on a computer is not super melodic. You know, that is perhaps not super beautiful. Yeah, not the most beautiful thing in the world. Though when I play the same notes on, say, a violin, a piano, and an alto sax, those clearly sound different. They have a different feel to them, even though they're all playing the exact same note. Their fundamental tone is, in all of those cases, exactly the same frequency. But the character that the sound has, the timbre that the sound has, where that's coming from is actually related to these harmonics. You know, so the idea, I guess we had a tuning fork. I should have brought a tuning fork. Whatever, the computer can do it. Right, so the idea, like with a tuning fork, is that when you play a tuning fork, you're getting just the single pure tone. It is only giving you that fundamental tone and nothing else. Versus something, and so it sounds very pure and almost a little unreal, not natural. Doesn't have any warmth to it, any context. It sounds very empty. A flute is kind of the next kind of level of that. A flute kind of creates a very pure sounding tone, though clearly it doesn't sound exactly like a tuning fork. So what's going on there is that a flute, when it plays the same note, it has that fundamental tone, but then it has some of those additional harmonics playing on top of it as well. You're not just getting 440 hertz, but you're getting 440 hertz plus some of the higher order harmonics on top of that wave. So the wave that ultimately comes out doesn't look like a nice sinusoid, but it has a little bit of, I might say, character, which as a result gives a different sound to the flute. versus a violin or a singing voice or a clarinet, they could all be singing the exact same note, but they sound quite different. And also, compared to a guitar string, they sound all quite different because they are creating different amounts of those harmonics on top of that fundamental tone. You could analyze this in this is called Fourier analysis, where essentially you take the sound that you hear from, say, a flute, that's playing G4. And there's, you can think of this plot, all these spikes, you can think of it as the amount of energy that is coming out, and the amount of waves that are coming out at that given pitch, that given frequency. There is a lot of energy coming out, and this actually is a logarithmic scale, so small vertical changes actually are quite dramatic. So there is a lot of energy when the flute plays G4. There's a lot of energy that comes out at that tone, which is why that is what we register, and why we associate that with a particular location on, say, on the scale. But the flute also has power in some of its harmonics. So you're seeing these other bumps are the harmonics that you could calculate with the formula we just wrote down. The formula we wrote down does not tell you how much of each harmonic you're hearing, but it tells you what those frequencies are. The construction of the flute, the material it's made out of, the way that the chamber is constructed, all those physical properties are working in a way that is, when you try to perturb the air and standing waves are set up inside the chamber, on top of that fundamental tone are also standing waves that correspond to some of the various harmonics, and they appear in different amounts. And as a result, that makes a flute sound different than, say, a violin, where notice it is playing the exact same note. Most of its power is peaked at G4. It reaches the highest kind of vertical value on the scale at G4. But the relative amounts of the other harmonics that appear in the violin are quite different than the flute. The fact that the flute really only has the lower level harmonics is what makes it sound kind of tinny and kind of closer to something like a tuning fork. Where the fact that there's all this energy in the higher level harmonics for a violin is what gives the violin a sort of richness that makes it sound slightly different. Actually, not slight, quite dramatically different from, say, a flute or a tuning fork. And then different ratios of these harmonics make a saxophone, make a piano, make a ukulele. For even though they're all potentially playing the exact same bass fundamental note. Which I think is kind of cool. Maybe there's a Jan term called the physics of music in the future. That could be fun. It would essentially just be some of this. All right. In the past, I've done the Doppler effect at this point, but we have simply run out of time. The Doppler effect is important to me. It plays a very big role in astrophysics because light also exhibits a Doppler effect. But perhaps it's not the most important thing for right now. Let's move on to thermodynamics. This will obviously be brief. We only have, at this point, 1.5 lectures left. The central concept of thermodynamics is, perhaps unsurprisingly, temperature. A study of, what makes something hot versus cold, which we quantify by saying this thing called temperature. But maybe you've never actually thought about it. What do we mean by temperature? When I say something is 100 degrees Celsius, what do I mean? What does that physically connect to? It could just be some quantity, some arbitrary quantity I measure. But this is a physics class, so that would be that'd be slightly anticlimactic for a physics class. The measure of temperature that we're going to focus on over these next two lectures is actually saying something about the internal energy of the system. The temperature, it turns out, is just a way to quantify what we call the internal energy. It allows us a way to say, it allows us to physically understand, like when I put something in the microwave and the temperature goes up for the object, even though, if you ever notice this, depending on the object you're heating up, it might be releasing steam or whatnot, but in a microwave, you can microwave something and then immediately stick your hand in the microwave and your hand is perfectly fine, even though the object you just heated up might be, extremely, extremely hot. Something is going on with the microwaves, being transmitted to the object in the microwave that causes it to heat up, which in physics we quantify by talking about this thing called the internal energy. It is essentially, by internal energy, essentially you can think of it as a measure of the random motions that make up the system, like in terms of when you're talking about, say, a gas, for example. A gas in a box has a certain amount of internal energy, which relates to the amount of energy it has as the gas molecules themselves just kind of wiggle around and fly around. We're going to be sticking with gases, I think, for these two lectures, just to keep things simple. Thermodynamics originated as a study of energy transfer. The idea, like a lot of our ideas behind what we now call conservation of energy, originated from the studies of thermodynamics by people like Joule's, which is why his name now, holds is the unit for things like energy. But a lot of his work was pioneered off studies of thermodynamics as well, in terms of quantifying the energy of a system, the internal energy of the system, how much energy is contained within the random motions that's going on. So I think, and then actually that developed into another branch of physics, which is called statistical mechanics. Which now it turns out that Thermo and Stat Mech are one and the same, but Stat Mech essentially gave mathematics and a very microscopic interpretation of the results from thermodynamics, and that once we understood that objects were comprised of many, 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 many small little atoms that were either constantly bombarding with each other, like in gases and fluids, or might be bound in structured lattices. By doing where if we really wanted to, we could write down F equals ma for all those billions upon billions of objects, look at the kinetic energies, look at the potential energies, and we would get the right answer. But of course, we do not have the computational power or patience to do that for, say, 10 to the 23 particles. So we can look at things globally in a more statistical sense, and it turns out that you can actually make incredibly, incredibly strong predictions through statistical arguments, which was the entire idea behind statistical mechanics, which then, after a couple breakthroughs, it was realized that StatMech could be used to perfectly represent everything that's going on in thermodynamics. A StatMech course, we say for the upper level sequence, but we can talk a little bit about temperature and energy transfer today and tomorrow. So today we're going to define temperature in the thermodynamics way. In the next lecture we'll define temperature in the statistical mechanics way and see how they connect to one another. The idea of temperature originated out of this idea that if I say have some object, this box, and I am in contact with it, I am touching it. The idea is that if we wait long enough, we will reach some sort of thermal equilibrium with one another. In which case we would say that the box and I are at the same temperature. And in thermal equilibrium, everything kind of just remains as it is. Versus if I were to say, take a piece of ice and hold on to the piece of ice, it would undergo a transformation. The ice would eventually melt and become a puddle of water that I am then holding in my hands. And if I were to wait long enough, the water would heat up. Well, we don't know that that's the direction things are going, but eventually the water would reach the same temperature as my body, in which case we would say that the two objects have come into thermal equilibrium with one another. My temperature and the temperature of the water match. You can use this as a way to define temperature, as a way of specifying that temperature is the quantity that is achieved when the objects are in thermal equilibrium. Which, if you think that this is meaningless, it's not, but it kind of is, in that this doesn't tell us how to write down a number. This doesn't tell me how I'm able to say that I am 97 degrees Fahrenheit or something like that. This gives us just a way of measuring, and essentially, how you might quantify this if you were to do the full logic experiment, is that you would then have to create some sort of object that had a well-defined or a specified temperature, where like I could have, like how for the MKS unit system, right, there used to be, a kilogram object that was stored in a vault somewhere, such that if we really wanted to measure everything's mass, we could do so relative to the kilogram. And everything is measured relative to that thing in the vault. Essentially, in this case, you would have some object that you would define to have a certain temperature, and use that to define your unit system. The triple point of water has typically been used in the past. Apologies to the chemist if I get this wrong. But the triple point of water is this point for I believe it's for atmospheric pressures. So, for typical environmental conditions like what we experience on the Earth, there is a temperature where water can both be a solid, a liquid, and a gas. It is possible that it can exist in all three states at this given triple point. Then if you increase the temperature a little bit, it makes a decision as to which of these it's going to be. If you increase the pressure, it makes a decision as to what it's going to be. This is defined to be 273.16 Kelvin. Actually, maybe the chemist could answer this. I don't know the history behind why this particular number, admittedly. I think it connects to the Celsius scale, because I think the Celsius scale really wanted freezing to be 0. And we'll see that this essentially is, when you translate this into Celsius, it is 0. So in this case, this Kelvin scale, quantified by Lord Kelvin, with a way to then assign, saying like, okay, we're going to call this set of conditions, this is going to be 273.16 Kelvin. Hotter things are going to be hotter than that, colder things are going to be colder than that, and people can come up with whatever refined scale they want to in a way of quantifying what differences in temperature mean. You know, the difference between 1 and 2 degrees Celsius is different than the difference between 1 and 2 degrees Fahrenheit, for example. Though the Kelvin scale is the one that's based in physics. The Celsius and the Fahrenheit scales really are based, kind of derived as a way of quantifying observations. There is physics behind the Kelvin scale. In that, for the Kelvin scale, so that is to say, in science, particularly in physics, all temperatures are measured by the Kelvin scale. When I quantify the temperature of an object, temperature of a star, temperature of the gas in the room, I always quantify in terms of Kelvin if I'm going to use it to do numbers. Kind of like how you always do everything in radians. You never do anything in degrees when you're plugging things into equations. Kelvin, you always do temperatures in Kelvin. Then the number has physical meaning, compared to if you were to plug things in Celsius and Fahrenheit. You wouldn't necessarily capture the physical trends like what we might see in the next 2 lectures. So the Kelvin scale has particular limits. 0 degrees Kelvin. Actually, sorry, 0 Kelvin. Degrees Celsius, degrees Fahrenheit, Kelvin. Not degrees Kelvin. I'm going to screw that up bunches. But technically it's just Kelvin. Notice there's no little degree signs that I'm drawing here. 0 Kelvin is called absolute zero. And essentially it's saying that this is the coldest possible temperature. In the Kelvin scale, you cannot ever go below absolute zero. Essentially, absolute zero is the definition. Since, thinking ahead, we're going to see that temperature connects to the energy that an object has. Essentially, an object would have to have 0 internal energy in order to possibly get at absolute zero. Any sort of energy at all would raise the internal energy of the system above 0 Kelvin. So we think of this as the coldest absolute possible temperature. That kind of anchors things down, and then the way that Kelvin came up with the graduated tick marks, what does 1 Kelvin versus 2 Kelvin versus 3 Kelvin stand for? How much difference is there between adjacent tick marks? He used the triple point of water to then identify, okay, I'm going to call this 273.16, and from that he was able to get his temperature scale. Versus the ones we are more familiar with, which is the Celsius scale, where 0 degrees Celsius is the freezing point of water. That's kind of one of the definitions of the Celsius scale. And then they say 100 degrees Celsius is the boiling point of water. And so that allows you to establish what each tick mark, on your temperature scale corresponds to, as you go from 0 to 100 or below 0 and above 100. And then there's the Fahrenheit scale, which was needed because they felt that the Celsius scale was not refined enough. Right, which 32 degrees Fahrenheit was the freezing point of water. And then, what is it? Gosh, now I'm blanking. 212, is that it? If I'm wrong, you'll see the video has been edited at this point. But then notice that there's more numbers between these two endpoints, so you can create a more refined set of tick marks that, there's less change between 1 degree in a change of 1 degree Fahrenheit compared to 1 degree Celsius, for example. So the relationships between them, really it's how you connect them to Kelvin, which is the physics one. So the temperature in Celsius, that one is the simplest. It's just the temperature in Kelvin minus 273. So for example, 0 degrees Celsius is the same thing as no. 0 degrees Celsius is the same thing as 273 Kelvin, for example. 100 degrees Celsius is the same thing as 373 Kelvin. Room temperature, which is like, I don't know, 20 degrees Celsius or so, is about 293 Kelvin. So I usually think of about 300 Kelvin is about room temp, to help orient yourself. Though that's admittedly a little hot. It's a balmy room temperature. Then the temperature in Fahrenheit, the relationship there is that it's 9/5 the temperature in Celsius plus 32 degrees. Did I write this down wrong? No, I did not. 0 degrees Celsius is 27. Yeah, okay. I did not write that down wrong. It is getting late. So in this case, something like 32 degrees Fahrenheit, you can then see if you plug that in. If you plug in 32 on the left-hand side, that corresponds to 0 degrees Celsius, or that corresponds to 273 degrees Kelvin. I think technically, right. I'm being a little sloppy here, in that, this 0.16 is supposed to also be, flying around there, but I'm just sticking with integers. It is usually good enough for our tasks at hand. Something like 50 degrees Fahrenheit is actually exactly 10 degrees Celsius. And then it's every 18 degrees Fahrenheit is every 10 degrees Celsius. And that's essentially what that 9/5 is telling you. 9 degrees Fahrenheit for every 5 degrees Celsius, or every 18 degrees Fahrenheit for every 10 degrees Celsius. And then there is the offset to make 0 Celsius 32 degrees Fahrenheit. So that is how you can define the temperature of a system. And again, the temperature is defining the internal energy. So if you put energy into the system, so suppose you have some object that is at some temperature T naught. The idea is that if you put energy into the system, where this is energy into the system, typically uses Q. It is called, unsurprisingly, heat. In that case, then the temperature might increase. The final temperature might go up as a result if energy is put into the system. If energy is taken out of the system, a certain number of joules are taken away from the gas or the water or whatnot. That causes the temperature to go down. This Q quantifies the transfer of energy. Or heat. Heat, unfortunately, is a little sometimes misleading because we say heat is the transfer of energy, which could mean you're putting energy in. It could also mean you're taking energy out. So the temperature could go down if you are doing, if heat is occurring. Yes, apologies for that. So the idea with thermal equilibrium and when two objects can have the same temperature means that if I have some object A and some other object B and they are in contact with one another, through that interface, heat can be exchanged. Maybe a hot object, which has a lot of internal energy, and you have a cold object, like a piece of ice. In that case, if we think of heat as a measure of giving energy from one thing to the other, energy can be exchanged between the two. Energy is always conserved as long as you take into account how it's being transported and what forms it's taking. They will eventually reach a point where they both have the same internal energy or temperature. In that case, A and B will stop transmitting energy to one another, and they will therefore be in thermal equilibrium. Thermal equilibrium, same T. We now understand this to mean that that energy is transferred in a way where energy goes from hot objects to cold objects, though that's not a given. That's not actually completely obvious of why that has to be the case, which we'll get a little bit into that, I think, next time. So what I want to end with is talking about different ways that energy can be I'll start. Yeah, let me do conductors and insulators, and then I'm about at time there. Then we can do phase transitions, and actually trying to put some numbers to this, specific heats, trying numbers of how you heat up water and change it into vapor and stuff like that. So, but it all comes from the fact that you have to be able to transfer energy between two objects. Some objects transfer energy much easier than others. We call them conductors. Some objects transfer energy very poorly, or resist the transfer of energy. We call them insulators. This depends on the properties of the system. This depends on kind of their molecular makeup and how easy it is if energy is being transmitted through kind of small, tiny little motions that are going on at the microscopic level. This depends very much on kind of the molecular structure and how easily energy can be transmitted from one sort of object to another. For example, here are two black plates. Let's move these. They are made of different materials. This is kind of a plywood sort of thing. This is more of a kind of marble stone. They have been sitting out on my desk this entire time, so they are both in equilibrium with the room. They are both at the same temperature. I would ask you to confirm this, but we are not in person, unfortunately. So the idea here is I can take a piece of ice, and I want to find two kind of roughly equal pieces of ice, and I will put them on the surface. A different piece of ice for a different surface. And the idea is to see what happens to the ice cubes as a result. A little bit of setup first. All right, so two kind of roughly equal sized pieces of ice. One on the wood, one on the stone. Again, the stone and the this kind of hollow wood start at the same exact temperature. So the ice is at 0 degrees Celsius for both. So I'm essentially setting up the same experiment but on two different surfaces. In this case, the surface, you might notice that nonetheless something very dramatically different is happening in terms of what you are seeing here. Maybe I'll throw it on this this camera as well. So again, I did nothing fancy, no tricks. The only thing that's different is the material that the ice cube is resting on top of. In this case, kind of the hollow plastic wood thing, and then the stone. So notice, one, essentially the ice cube has completely vanished by this point, after like 1 or 2 minutes. Versus nothing really has happened at all with this one. Very little water has accumulated from the ice changing temperature. I would say it's actually more likely that water is just from the air interacting with the ice and not so much this material interacting with the ice. Versus in this case, the stone has essentially made the ice completely melt. What this is showing is that this material is a very poor conductor. It is a very good insulator. It is hard for all the thermal energy, the fact that this thing is at room temperature, much hotter than 0 degrees Celsius. But it is having a very challenging time giving any of that energy to the ice cube. And so as a result, the ice cube remains essentially completely solid. Versus in this case of the stone, which is a very poor insulator, very good conductor, in which case the thermal energy, the higher temperature it has a lot more of internal energy. It has a much easier time giving some of that thermal energy, some of that gives some heat to the ice cube, and as a result, they approach thermal equilibrium with one another much faster. If we were to wait long enough, eventually the stone in this water would reach the same temperature. You can actually feel that the stone has gotten a little bit, definitely clearly gotten colder as a result. Because it's given away some of its energy to that ice cube and has completely melted it. Whereas in this case, barely anything has happened. So, insulator, conductor, easy to give away energy and to come into thermal equilibrium. Very hard for energy to be transferred between two objects when one of them in particular is an insulator. So, next time we will get a little bit more quantitative, look a little bit more at the microscopic level of things. And it'll be mostly, the beginning will be a little quantitative in terms of quantitative calculations I might expect of you. But the end will get a little bit more kind of farther out there, where the idea is to just kind of get a gist of what's going on. All right, and then we're done.